All right, let's continue our discussion of redox reactions. We're going to talk now about the ion-electron method. The ion-electron method refers to a method for writing the net ionic equation for a redox reaction that's happening in aqueous solution. Okay, and the way you would do this is you first identify the species, that means the ions or the molecules that are actually involved in the half reactions. Okay, so you need to identify your half reactions. Then you balance your half reactions. And then you combine your half reactions so that electrons lost equals electrons gained. So let's take a look at this unbalanced redox reaction. We looked at this last time, so we're going to try to balance it this time using the ion-electron method. Okay, what would be your unbalanced half reaction for this? What did we say the oxidation numbers were? Your copper went from +2 to, from 0 to +2, right? And your nitrogen went from +5 to +2, right? So what's our half reactions? Your copper became copper ions with a +2 charge. That's the only thing we write. Okay, we don't write the whole copper nitrate thing, because what do we know about copper nitrate in solution? When we're writing ionic equations, we'll have to separate this copper +2 nitrate. So the only thing that's really involved there as far as that half reaction is concerned is the copper ion. So that's your half reaction. And then what do you call this half reaction? Oxidation or reduction? Going from 0 to +2, this is an oxidation, right? Increased oxidation number. What about your, in fact, we already seen that this was what? 2 electrons lost, right? So you know that you're going to have 2 electrons over here. And what's the other half reaction? HNO3 to NO. But what do we know about HNO3? It's one of the 6 strong acids, so in aqueous solution it's completely dissociated, so we don't write it as HNO3 when we write net ionic equations. What do we write it as? H plus nitrate, right? So it's H plus nitrate, but H plus is not involved in the redox. It's just the nitrogen that's reduced. So the only species that we write when we write our half reaction is NO3 minus, at least at the outset. Okay, we'll find later that we're going to have to add back that H plus, but we just write the species as a first step. We just write the species that are actually involved in the reduction and the oxidation. What happened to the nitrate? The nitrogens in the nitrate got reduced. The ones that got reduced ended up being part of the NO molecule. So that is your other half reaction. This is your reduction. Okay? So those are your 2 half reactions. So what you do is you balance those 2 half reactions, and then you combine them so that electrons lost equals electrons gained, and you got your overall equation. So how do you balance the half reaction? Here's a general strategy for balancing half reactions. Let's focus first on reactions happening in acidic solutions. First, you have to balance all the atoms besides your hydrogen and oxygen. You balance the hydrogen and oxygen last, okay? So once you get all the atoms balanced, you balance your oxygen by just adding H2O to the side that needs it, okay? And then you balance the hydrogen by adding H plus to the side that needs it. And then finally, you balance charges by adding electrons. Okay? Now, if you've already identified, since presumably you've already figured out how many electrons lost or gained anyway, you know how you can actually do this ahead of time. But if you can look at charges just to verify that the electrons lost, electrons gained actually matches the change in oxidation number. Okay, so let's illustrate that with this. Perchlorate gives you Cl2 in acidic solution. So that's my half reaction. I've identified the species involved. Okay. Now, what was the first thing we need to do? balance all the atoms besides oxygen and hydrogen. So what's the only atom here that's not hydrogen or oxygen? Chlorine. How do I balance my chlorine? I need 2 there, right? 2 chlorines on the left, 2 chlorines on the right. So now, next step, balance. Once you balance your chlorine, you balance your oxygen now, right? How do I balance oxygen? How many oxygens do I have on the left? 2 times 4, that's 8 oxygens, right? So I'm going to need 8 oxygens here. On the right. How do I get 8 oxygens on the right? I add water. So how many waters would I need to add? I add 8 waters. For every oxygen I need, I add a water molecule. Okay? Now, I balance my oxygen, right? 2 times 4, 8 on the left, 8 times 1, 8 on the right. Next step, balance hydrogen. How many hydrogens on the left? No hydrogens. How many hydrogens on the right? 8 times 2, 16. So I add 16H plus to the side that needs it. So all my atoms are now balanced. The last step is balance charges. Okay? Let me fix this up. Balance our charges. What's 16 times positive 1? That's positive 16. What is 2 times negative 1? Negative 2. So what's the total charge on the left? Positive 14, right? What's the charge of chlorine? Neutral molecule, 0. What's the charge of water? 0 times 8, still 0. What's the total charge on the right? 0. Charges must be the same on both sides. So how do I make charges the same? I add electrons. To which side should I add my electrons? Oh, you want to add electrons to the more positive side, right? So I add 14 electrons to this side. So to this one, let me move this. I can't move it. So to this side right here, I have to add 14 electrons. Okay. So let me rewrite this. My balance equation is, my balance half reaction is 14 electrons plus 16H plus 2 perchlorates, 2ClO4 minus, gives you Cl2 plus 8H2O. All right. Let's make sure. We have 2 chlorines, 16 hydrogens, 8 times 2, 16 hydrogens, 2 times 4, that's 8 oxygen, 8 times 1, that's 8 oxygen. Total charge 14 on each side. Now, let's verify that the electrons lost. Is this, by the way, is this reduction or oxidation? Let me just do a quick check. A, is this reduction or oxidation? Is it A, reduction, or B, oxidation? See if you remember. This half reaction that I just wrote, is this a reduction or an oxidation half reaction? It is reduction. Very good. Oh, here's another memory aid I've developed for this. Reduction, remember, is electrons gained, right? It appears on the left. Electrons appear on the left. Wiggle. I like making stuff out like that so I can remember things on a test. Okay, so it's reduction. Okay, so electrons gained. Let's verify using oxidation number. What's the oxidation number? Remember what got reduced here? This one, right? 2ClO4 gives you Cl2, right? What's the oxidation number of chlorine in ClO4? What did we say oxygen was? Oxidation number of oxygen is -2 times 4. That gives you -8. So what must the chlorine be here? Let's call it X. Plus -8 equals -1, the overall charge. What's the oxidation number of chlorine in perchlorate? +7. What about Cl2? What's the oxidation number of chlorine? This is a pure elemental substance. Oxidation number is 0. So you went from +7 to 0. That's 7 electrons gained. Is that consistent with 14 electrons here? Yes, because there's 2 chlorines in this half reaction. So 7 electrons gained, that's per chlorine, okay? For every chlorine. And since you have 2 chlorines in this half reaction, then that should involve 14 electrons gained. Okay, so that's how you do it. So that's how you do it in acidic solution. Now, what if your reaction is actually happening in basic solution? Then you don't use H+, you use hydroxide. So you balance using H2O and hydroxide. So what you do is wherever you find, one strategy is to balance it as if you were doing it in acidic solution. And then wherever you see the H+, just replace that by H2O and then add hydroxide to the other side, because that will take care of that will get rid of any H+ in your balancing half reaction. Okay, and you may need to simplify it because water might appear on both sides. Let's illustrate that with what we just had earlier. What was our balance equation? 16 and 2, 1 and 8. Okay, 14 electrons. Okay, and 14 electrons plus 16H plus 2 perchlorates gives you how much? Cl2 plus 8H2O. That's what we had, right? Let's just make sure. Yeah, that's what we have. So if this were to actually happen in basic solution, then I don't want H+ in my half reaction. Basic solution, I should have more hydroxide. So I'm going to replace this by 16 waters. And then every H+ that I replace with a water, in essence, what did I do to my H+ to change it to a water? I combine it with a hydroxide, right? So if I had 16 of these H+s combined with all hydroxides to make water, then I have to add 16 hydroxides to the other side. Okay? And so my balanced half reaction in basic solution would be 14 electrons plus 16 H2O plus 2 perchlorates yields Cl2 plus 8 H2O plus 16 hydroxides. Now, one last step you need to do here is to simplify. You see 16 waters here and 8 waters here. What do you do with that? That means that's a net loss of just 8, right? You start with 16, you end up with 8, so you can just get rid of this 8 and then replace that by 8. So that's the final answer here. You would have 14 electrons plus 8 H2O plus 2 perchlorates yields Cl2 plus 16 hydroxides. That's your balance equation. Let's verify that it is in fact balanced. Chlorines, you've got 2 on each side. Hydrogens, you have 8 times 2, that's 16. That's 16 hydrogens. Oxygen, you have 8 plus 8, that's 16 oxygens, and you have 16 oxygens right here as well. So it's balanced. As far as charges go, this is -14 plus 0 plus 2 times -1. That's a total charge of -16 on the left. And the total charge on the right is also -16. 16 times -1. Okay, you have 16 of those hydroxides, it's -16. So that's your balanced half reaction. Okay? Now, There is an alternative strategy for doing this, and this one, some teachers prefer this because they don't like the idea of putting H plus when it's in basic solution and then making the adjustment later. So you can actually just balance using hydroxide and water at the outset. Okay, so let's illustrate that second strategy with this. Whichever one you feel comfortable with, you can use. I'm fine with it. I only care about the final answer, that it's balanced. Okay, so here you have C. Of course, you need to know how to do it. ClO4 minus gives you Cl2. What should I do here? First step, balance all atoms besides oxygen and hydrogen. So what do? I need 2 chlorines, right? And the next step is this. To the side with excess hydrogen, you add hydroxide. Why? Because that excess hydrogen, combine that with hydroxide, will give you water on the other side. See? So do I have any excess oxygen here? I don't, so I can't use that. So let's go on to the next step right here. If you have an excess oxygen on one side, okay, combine that with H2O on that side, add more H2O to that side, what happens to the other side? You got 2 oxygens and 2 hydrogens. To balance that on the other side, you add 2 hydroxides to the other side. Okay, so for every extra oxygen, I add water. So which side has an extra oxygen here? Left or right? 2 times 4, I have 8 oxygens here, right? No oxygen here. So how many waters do I add to the left side? Every oxygen extra, I add a water. So I add 8 water to this side. And then what do I add to the other side? Twice as many hydroxide. So 8 times 2, 16 hydroxide. Okay, and then the final step, you have to balance your charges, and you'll find that you're going to have to add 14 electrons to this side. And that's the same balanced half reaction we saw earlier. Okay, so that's how it's done. Same thing right here. Okay. Once you balance your half reactions, then you can just combine them to get your overall net ionic equation, and you may have to simplify things again in the end if you have common terms on both sides. Okay, so when you combine your half reactions, make sure you balance electrons lost and gained. So let's look at an example of 2 half reactions. Here's one, and here's the other one. Okay, so which of these is the Okay, let's do a little review. Which of these, A or B, which one is oxidation? Okay, correct answer is A. Loss of electron is oxidation. So this has a loss of 1 electron. This has a gain of 2 electrons. So every time A happens, that only involves 1 electron. B can't happen because B only needs 2 electrons, right? So what do we have to do? A has to happen how many times for B to happen once? That's least common multiple of 1 and 2. 2, right? So I multiply this by 2. I multiply the second one by 1. So A has to happen twice so that you can get the 2 electrons you need for B to happen once. So before I combine these two, what I need to do is double up my oxidation. I'm going to say 2 sodium gives me 2 Na plus 2 electrons. And then my second half reaction is the same. 2H2O plus 2 electrons gives me H2 plus 2 hydroxides. And so now I add those two, combine them. What do I get? 2 sodiums plus 2 waters plus 2 electrons. That's on the left. And on the right, I have 2 sodiums plus H2 plus 2 hydroxides. plus 2 electrons. Of course, your electrons will just cancel because we made sure that they cancel. Okay? So you don't even have to worry about that. Balance electrons lost must equal to electrons gain, and so your balance equation would be 2 sodiums plus 2 H2O yields 2 this is Na plus, sorry, 2 Na plus H2 plus 2 hydroxide. This is what happens when you put sodium metal in water. You get sodium hydroxide and you produce hydrogen gas. Okay? So that is how you construct an overall balanced equation for a redox reaction in aqueous solution. Okay? Now, let's talk about standard reduction potentials. The most commonly observed half reactions in aqueous solutions can be found in a table of standard reduction potentials. You should have one in your textbook, and you should find a whole bunch of them on the internet. One website that I like to go to that has all that information is do a search for the National Physical Laboratory in the UK. Okay, NPL UK. Okay, so it's npl.uk. Let's see, NPL UK. National Physical Laboratory. Do a search for that in the UK. Okay. Do a search for. Let's see. Let's do electrochemistry. Okay, since we're doing electrochemistry, npl.uk. Let's see. Let me try to remember. Oh, AYELABY. Okay, npl.uk. That's the address. So it's www.kayaybY.npl.uk.npl.co.uk. CO is what they have. It's like their .com over there. Okay, a company, corporate. Okay, and so if you go to that website, okay, that is where you find a lot of data. So you go to the table of contents. Okay, and this is where you find lots of information, not just for electrochemistry, but for other stuff. So hit chemistry right here, the link to chemistry. You'll notice there's sections on the elements, properties of organic, inorganic compounds, vapor pressures, critical constants. You remember when we talked about the van der Waals equation, we say you can calculate those from critical constants. Okay, properties of solutions. If you look at this one, it tells you about solubilities of gases in water. Okay, so that gives you Henry's law constants. Okay, properties of chemical bonds. Okay, dipole moments, dipole lengths. That's a nice place to get that information. Let's see, what are we looking for? I got sidetracked. Electrochemistry, right? So if you click on electrochemistry right here, okay. Oh, by the chemical thermodynamics, section 3.10. There's a lot of information there. Electrochemistry, where is it? Electrochemistry right here. Standard electrochemistry, standard potentials. Okay, let me blow this up. Fine. Under electrochemistry, look at standard potentials. You have a list of all the most commonly used half reactions. They're called electrode reactions. Okay, for reasons that will become clear later. So these are all listed as reduction. Notice. They're all listed as reduction. You have electrons on the left side. And what you have tabulated here, what are known as a standard reduction potential. So for example, the standard reduction potential for calcium ion is negative 2.84, and the unit here is in volts. Okay? So that's a standard reduction potential. So, what about H plus, this, by definition, this is given as value of 0. 2H plus 2 electrons gives you H2 gas. That's 0 volts. And fluorine has a standard reduction potential of 2.87. And lithium is negative 3.04. Let's verify those numbers, see if I got them right. Lithium is negative 3.045, okay, volts. And where is hydrogen? Should be 0 somewhere. So when you cross these are listed from most negative to most positive. So 0 is somewhere in between, right here. By definition, this is 0 exactly. 2H plus. So the standard reduction potential of H plus to H2 is 0 volts. Okay. And what else did we have in our example? Fluorine. Fluorine would be the most positive. Standard reduction potential. I don't have it here. It must be somewhere else. Oh, there's more. Doesn't have everything, apparently. But you should be able to find a whole bunch of other sources on the internet, and pretty much most of them are reliable. Okay. So anyway, what do these standard reduction potentials mean? The number here, given in volts, tells you the likelihood of that reduction. Okay. The more positive that value is, the greater that tendency for that to occur. Okay. So if you compare half reactions, if you have two half reactions, okay, of these three, then which is the most likely to occur, has the greatest tendency to occur? Is it going to be A, B, or C? Okay, so we say that F2 is the most likely to get reduced, comparing the reactants, H plus, F2, and lithium plus, okay? H plus, F2, and lithium plus, we say F2 has the greatest tendency to get reduced, okay? Now, since reduction is another terminology I forgot to mention last time, since reduction, when something gets reduced, causes something else to get oxidized, right? So if fluorine has a great tendency to be reduced, that means it has the greatest tendency to cause something else to get oxidized. So we say, so greatest tendency to be reduced, and we can relate that to the electronegativity. Fluorine likes to accept electrons, right? It's the most electronegative. Gaining of electrons is reduction. We can also say that is the best oxidizing agent. If something gets reduced, if you get reduced, you're causing something else to get oxidized. So something that's reduced, we say, is an oxidizing agent. Something that gets oxidized is a reducing agent. So if you do hear those terminologies, make sure you understand what it means. When you say oxidizing agent, that is something that is getting reduced. Okay, when you say reducing agent, you're talking about something that's getting oxidized. So we say, since these are all written as reductions, okay, you're comparing the ones on the left, we say then that among the reactants that are shown here, H plus, F2, and lithium plus, F2 has the greatest tendency to get reduced. Okay? So it's the best oxidizing agent among these three. All right. Now, if you write the half reaction in reverse, you write it as an oxidation instead, then you can define what's called the standard oxidation potential. Okay, it's just the negative of the standard reduction potential. So here we looked this up earlier. Okay, The reduction potential, or F2, is positive 2.87. If I were to flip this, I have 2 fluoride instead on the left and F2 on the gas. What is my oxidation potential? It's going to be negative 2.87 volts. Okay, so if you flip your half reaction, you get, instead of the standard reduction potential, you get the standard oxidation potential. Okay, so if I were to flip the other one, what's the other one? Let's say H2. H2. Let's try the other one, lithium. Lithium gives you lithium plus electron. So if I were to do lithium, gives me lithium plus electron. That's written as an oxidation. Okay, you won't be able to find any oxidation potentials online or any handbooks anymore because everything is tabulated as standard reduction potentials. So if I look this up, I'm not going to find it. I'm going to find that the reduction potential of lithium plus is negative 3.04. So what's the value for the oxidation potential? What's the negative of negative 3.04? It's going to be positive 3.04. Okay, so if I were to compare fluoride versus lithium, okay, in these half reactions they are oxidized, right? So if they're oxidized, what do you call them if they were oxidized in a reaction? You would call them the reducing agent. So which one is the better reducing agent? Is it A, fluorine, or B, lithium? I mean fluoride, F minus, or B, lithium. Which one is the better reducing agent? In other words, which one has a greater tendency to get oxidized? You don't even have to look up these numbers. What do you know about metals? They like to give away their electrons, right? Metals have a greater tendency to lose electrons. Metals have a greater tendency to get oxidized. So lithium has a greater tendency to get oxidized. That is your better reducing agent. Let's see how we did. Good. All right. Now, one thing you have to realize is that redox potentials are intensive properties. That means, okay, even if you double your coefficients in your half balance equation, this potential remains the same. So here, if I were, we looked this up earlier, right? If I were to ask you what is the reduction potential for this half reaction where I doubled all the coefficients, it's the same thing. Okay, so it's an intensive property. Now, a volt, as a comment about a volt can be defined as a joule per coulomb. Okay, the equivalent unit for a volt is a joule per coulomb, an energy unit over a charge unit. So you can think of a volt or a voltage or a potential difference as the ratio of the energy change when a charged particle moves between 2 points to the charge of the particle. So energy that the charged particle will gain or lose as it moves between 2 locations, okay, divided by the actual amount of charge. It's energy per unit charge. What do you know about electrons? If an electron moves to a positively charged plate, what happens to it? If an electron moves that way, positives and negatives attract, right? So what happens when an electron moves towards a positive plate? It speeds up, right? You see something attractive, you start running faster, right? So it speeds up, it gains kinetic energy. So the energy that's gained divided by the charge of the electron would be the voltage between those 2 locations. Okay, so if you go from one location to another, so that's called the voltage or potential difference. The charge of an electron, if you recall, is negative 1.6 times 10 to the negative 19 coulombs. Okay, now since we generally have to deal with moles, a mole of electrons would be Avogadro number of electrons. So if you multiply that by the charge of each electron, Avogadro number times the charge of each electron will give you 96,500 coulombs, okay, or 96,487 to be more precise. That is known as the Faraday constant F. Okay, so that's 96,500 coulombs in a mole of electrons. Why are we talking about moving electrons? Because we're going to talk now about taking advantage of redox reactions, okay, as reactions that involve electron transfer, right? Well, if you carry out your reactions in separate compartments, okay, you can have the electrons travel through a wire from one compartment to the other. Then that allows you to harness energy from your reaction in the form of electrical work. And so what kinds of benefits can we draw from that? You can run electrical stuff, basically. Your everyday battery is a container that has a redox reaction going on inside it. So when electrons come out of the negative part of your AA battery and it goes to the positive terminal of your battery, okay, remember, if you've looked at your battery, you'll see one side is marked negative, the other is positive. Electrons come out of the negative terminal and go to the positive terminal. And so if you hook this up with a wire, what happens? Your battery heats up and explodes. Why? As the electron travels from the negative to the positive, they gain energy, right? So if you don't dissipate that energy, it becomes heat. So you put a load on your circuit so you can use it to like light up a bulb or something. Okay, so you have to have some resistance. Otherwise, if there's no resistance, you have what's called a short circuit. The difference between the negative and positive terminals of your typical AA battery is 1.5 volts. Okay, so how much energy would be gained by a mole of electrons as they go from the negative terminal to the positive terminal? What would be the answer? 1.5 volts is what? A joule per coulomb, right? How many coulombs do we have in a mole of electrons? 96,500 joules per coulomb. 96,500 coulombs per mole, right? Per mole of electron. So coulombs cancel out. So what's 1.5 times 96,500 joules? 1.5 times 96,500. That's 144 kilojoules, 145 kilojoules. About 150 kilojoules, okay? That's how much energy is gained by a mole of electrons. So that energy that can be transferred to something along the way, like it could be used to light up a bulb, okay, or turn a motor. Okay. Predicting spontaneity. Standard cell potential, okay, for a reaction, for a redox reaction, you can look at the standard reduction potential and the standard oxidation potential. If you add those two up, you get what's called the standard cell potential. Okay. Now, this is really the negative of the reduction potential that you look up, right? Because you have the numbers that you have to look up would be reduction potentials. Okay. So keep in mind that when you say plus here, okay, we're assuming that we're flipping what we look up. Okay. If you don't flip what you look up, then you subtract. Okay. So under standard conditions, the standard cell potential for a spontaneous reaction is positive. So a standard condition simply means that all the reactants and products are present and have activities equal to 1. Okay, so that means your reaction quotient in a standard, under standard condition is 1. Okay, when all the activities are 1. So let's take a look at this one. Is the following reaction spontaneous under standard conditions or not? What are the half reactions here? The copper ends up being copper solid. Copper ions end up being copper solid. Your standard, this is oxidation or reduction? Electrons on the left. That's reduction, right? Right? Now, what do I do for silver to silver plus? What's my standard? So my reduction potential here is plus 0.34 volts. That's what happens to my copper. What happened to my silver? It's oxidation, right? What's my oxidation potential? Is it 0.8 or negative 0.8? Look at this expression right here. That's also reduction, right? So if I flip it, I make it oxidation. Look, I actually flipped it. My silver solid is on the left side of my actual reaction here, my given reaction. So my standard oxidation potential would be negative 8.800 volts. So what's my total standard cell potential then? What is positive 0.34 plus negative 0.8? 0.34 minus 0.8 is negative 0.46. What does that tell me? This reaction, as written, is not going to be spontaneous. It's not going to occur. Okay, this is a non-spontaneous reaction. Okay, in other words, if I were to put silver metal in a solution that has copper ions, I'm not going to get copper metal and have my silver metal dissolve in it under standard conditions. Okay, but what if I flip this reaction? If I write it the other way, if I have instead copper and I put it in a solution of silver ions, will it give me copper ions plus silver metal? What's my standard cell potential for this? You're going to have to flip all your numbers, right? So now this is going to be equal to positive 0.46 volts. So this means that if I have copper, okay, I put it in silver, in solution that has silver ions, I can generate silver metal out of that mixture under standard conditions. Okay? So that would be a spontaneous reaction. Now, what I can do is I can carry out these two reactions in separate compartments so that I can allow the electrons to travel through a wire. And what I've made is called a galvanic cell, or in everyday language, a battery. Okay, a battery historically is actually a series of galvanic cells. Okay, a battery means a series of things, but over time it's been used to just refer to just one cell, your AA battery, for example. Okay. Now, cell potentials, one thing you have to realize is that they do depend on the reaction quotient. That's why I kept emphasizing standard conditions in the previous slides. Okay, so, and the way they depend on the standard condition is given by the Nernst equation. Cell potential is equal to whatever the standard cell potential is minus RT over NF times the natural log of the reaction quotient. This is the same reaction quotient we talked about when we talked about equilibrium. Okay. Now, at room temperature, which is 298 Kelvin, okay, then the cell potential is equal to the standard cell potential minus this RT over NF, okay, and then if you change instead of a natural log, you take the base 10 log, this expression becomes 0.059 over N. So that's called your Nernst equation. What's the importance of this? This will allow you to determine what the voltage is going to be. If you were to set up, okay, your two half reactions in separate compartments, and you measure the voltage between them, that's what this E cell is. The cell potential is the voltage that you can get out of your battery when you set up your half reactions in separate compartments. Okay, so for non-standard conditions, your cell potential will be positive for the spontaneous reaction. So you know which reaction will be happening as your battery discharges. So when you say your battery is discharging, what's happening? As a battery discharges, electrons come out of the negative terminal and go to the positive terminal, right? So that's a sign of a reaction going on inside the battery. Okay. So as it discharges, its voltage is going to be changing. So that cell potential is going to be changing. Why? Because your reaction quotient Q here will be changing. Okay, you'll be forming more products, right? So eventually, when it's fully discharged, your cell potential will have reached, your reaction will have reached equilibrium. What happens to the cell potential at equilibrium? It becomes zero. Okay? So when you have a dead battery, it's no use to you, right? So let's predict if this reaction is going to be spontaneous or not. If your silver ion concentration is 0.01 and copper is 0.01, we'll just assume those are your 0.1. Let's assume those are your activities. What do we need to do here? What did we say was the standard cell potential for this? We did this earlier. Copper ion plus silver. This one. We knew it wasn't spontaneous under standard conditions, and we found that cell potential to be negative 0.46, right? Our standard cell potential for this, we found it earlier to be negative 0.46 volts. How do we solve for the actual cell potential? If we're not at standard conditions, we're going to say it's E naught cell minus 0.059 over N, okay, log of the reaction quotient. What's our reaction quotient here? Remember how to construct reaction quotient? Products over reactants. What's the activity of copper solid? Activity of a solid is 1. What's the activity of an ion in solution? That's the concentration of silver. Okay, divided by activities of the reactants. By the way, coefficients here are 1 and 1, so you raise this to the power 1. Activity of silver is 1, metal, solid. Activity of copper ions would be concentration of copper ions. All right, so that's how you do that. So what's our standard cell potential? Negative 0.46 volts plus 0.059 over N. What is N? N is the number of moles of electrons transferred per mole of reaction. Okay, so let's go back to this expression right here. How many electrons are transferred per mole of reaction? 2, right? This happens twice. Every time this happens once, your reduction of your oxidation of your silver happens twice. So 2 electrons transferred. N is the number of electrons transferred in your balance equation. Let's take a look at this equation right here. Here's your way to figure out your N. From copper plus 2 to copper, that's 2 electrons gained. Okay? There should be a 2 there. I forgot the 2. It's not balanced. To balance it, you need the 2 there, right? And that's 2 electrons lost. So N is equal to 2. So if N equals 2, so I divide that by 2, and then take the log of, what's your silver concentration? That makes a big difference now. There's a 2 there, so that should be squared. Okay? And your silver right here should be squared, but 1 squared is the same thing. So log, what's the silver concentration? 0.01. So that's 0.01 squared divided by copper concentration is 0.1. So that's 0.1 right there. So our cell potential is negative 0.46 volts plus 0.059 divided by 2 log of, what would this be? That's 10 to the negative 4 over 10 to the negative 1. So that's 10 to the negative 3. Okay. What's log of negative 3? It's negative 3. Okay. Log of negative 3. -3, take the log. Oops. 10 to the -3. 1 times 10 to the -3. Take the log. It's -3, okay? The log of 10 to the x is x. Okay, so this gives you how much? -3 times 0.059 divided by 2. That's -0.0885. And this is -0.46. So just keep those sig figs there. So even more negative, -0.55. Okay, volts. Even less spontaneous. So the reverse would be even more spontaneous. So if the forward reaction is non-spontaneous, that means the reverse is non-spontaneous. So if you set this up as a galvanic cell, okay, as where you separate your reduction and oxidation, you're still going to get a current, but not the way you would expect it. It's the other reaction that's going to happen. You're still going to get a voltage between them. And so we're going to talk about galvanic cells next time. Okay? I think that's what the next slide is all about.